Thank you very much for still sticking around on Friday afternoon. I take it you've all listened to David Brumley's keynote and know that this is the session where you learn how to make the money. That's why we're doing web stuff here. As a first disclosure, Rasoul was the student who did all the work that went into this paper and into this presentation. Unfortunately, he couldn't make it, so you're stuck with me and have to listen to my presentation instead. All right. As we've heard before, web applications are prevalent, prolific, and they're insecure. I pulled this data from W3C Tech yesterday, and it shows that about 76% of all web servers run on their backend PHP. So, target-rich environment. Moreover, within PHP, there are some heavy hitters. So, for example, WordPress alone is responsible for 43% of all websites that you can access on the internet. Pretty sweet. There are some other big ones in there, Drupal, Joomla, you name it. And they're insecure, right? So there are hundreds of known vulnerabilities, or known CVEs, rather, I should say, for WordPress. There is, for Drupal, we had this sequence of vulnerabilities that had names, like the side channel people. So Drupal getting 1, 2, and the terrible sequel 3. So important things to find and cure. And as Robin mentioned in his presentation in the very beginning, one way to go, for example, about cross-site scripting vulnerabilities is to do a data flow or taint analysis. And a very quick primer, what do we need for data flow or taint analysis? Well, we need to understand where is attacker-controlled data entering the system. So for PHP, you might look at the superglobals, get or post, or some of the other avenues that attacker-controlled data can get into the system. As a second step, you need to understand that if attacker-controlled input gets to a sensitive sink, then bad things will happen. And so here we have a couple of examples. If attacker-controlled input gets to the system API function in PHP, bad things will happen because then you have command injection. You get cross-site scripting or reflected cross-site scripting, another injection-style vulnerability if you get attacker-controlled input to the echo API function, and if you call unserialized, you get what's called a PHP object injection vulnerability. We don't want that, and so for our data flow analysis, what we do is we track whether attacker-controlled input from any of the inputs labeled in 1 can reach the sinks, any of the API methods labeled in 2. If that happens, then there's something to look at, right? So that's how we can detect potential bugs and vulnerabilities. There are other systems out there that exploit that. So just very quickly, these might go and hook into sensitive functions, track how attacker-controlled data moves through the rest of the application, and then identify available gadgets specifically for the PHP object injection to then fire off exploitation. So this is just very quick, and just for symmetry's sake, because it turns out that for detection as well as exploitation, we need like this notion of sensitive APIs, sensitive functions. And so in our data flow analysis, these are the sinks. And so one of the questions that we wanted to ask with our system is, well, how do you find those sinks? And how can you be reasonably sure that you actually found them all, right? So looking into related work, lots of papers have been doing static dynamic taint analysis on PHP, including my own work for almost 2 decades ago. And the observation there is that most systems and most papers that are out there, they're all great, but they mainly rely on a manually created list of what your sinks are. What are your sensitive APIs, right? The PhD student digs through PHP. They go through all the pain and suffering. They figure out that, for example, the 3 APIs that we had on the previous slide, these are bad. And I learned the hard way, by the way, there is also the mail API in PHP, which is a command injection sink. You have to learn this really hard because no one will tell you the documentation is incomplete, so it's expert knowledge, right? And then we have approaches that do scanning of a natural language processing of the documentation. So you get some set of sinks. The question that we had, can we do better than that? And specifically, we were looking for a way to automatically, objectively, and without expert knowledge or bias, come to a set of sinks that is defensively complete. Which brings us to our system, Argus. And so Argus is this principled and systematic approach to identify sensitive PHP functions, PHP API functions, that lead to injection vulnerabilities. As a very simple example for illustration, the box that we have here should illustrate the PHP interpreter in its entirety. And at the top, the interpreter exposes the PHP API. So there's various functions that web applications can use, the echo function, the unserialized function, many, many more, of course. And so if we give input to the echo function, The echo function internally calls the parse parameter function, and at the end of the day, there's this one function in all of the PHP interpreter that is responsible for reflecting or for outputting HTML code rather that goes into a return buffer that gets sent to the client. That's the PHP output write. So PHP output write is not an API, it's an internal function of the PHP interpreter itself. For unserialized, it looks very similar. First, we call parse parameters, and then internally there's this one function, this PHP var unserialized, that will take your serialized stream and inflate a PHP object from that. And then there's other functions. Print R, for example, will directly invoke or more or less directly invoke PHP output write. And the MD5 file function, because why not, will implicitly also deserialize your input. And so essentially what we're trying to ask is, if we know these internal functions that are sensitive for our injection vulnerabilities, can we figure out all the API functions that, if they receive attacker-controlled data, will then cause problems? That's the type of question that we want to answer. Why do we even bother, right? Let's say we are successful, we know this, we learned this, so what did we gain? Well, if we look at our three-step approach of how Argus does that, we'll go through the 3 steps in a little bit more detail in the following slides. We first generate the call graph for the PHP interpreter. In the second step, we perform a reachability analysis. And then in the third step, for Argus, we validate the identified flows or the identified reachability relations. And then I put this delimiter line there because now Argus is essentially done with its job. What do we do with the output of Argus is we take it and we improve systems that others have created already, right? So there is vulnerability detection, vulnerability automatic exploitation tools that we can improve by simply taking the output that our system produces. And so that's essentially the final step that's outside of the purview of the Argus system itself, extending and improving existing systems. All right, let's go through these 3 steps in a little bit more detail. In the first step, as I mentioned, we create a call graph of the entire PHP interpreter. We start off with a static representation of the call graph. We do some off-the-mill static analysis there. But then it turns out that because PHP is so highly dynamic, there's a lot of call edges that statically are really hard to derive. And so what we do to combat that is we use PHP's excellent unit test suite. So again, if you remember back to David Bromley's keynote, who is writing unit tests, it turns out the PHP developers, for all the trouble that is their language, they have excellent unit tests or excellent test suite for their PHP interpreter. The test suite covers around 70% line coverage of the entire thing, I believe. And so we run that, instrument the interpreter to keep track of call and function invocation relations, and then augment our static representation of the call graph with the calls that we get dynamically. It's a very simple example. Why do we need this? How do you open a file in PHP? Very easy. You call the fopen API, right? Fopen, you open a text file, great. Fopen, you open a targz, everything's great. Now the nastiness of PHP, you do fopen HTTP, some resource of the web, exactly the same API. You can do the same thing for FTP if you love old protocols. All goes through the same API. Internally, PHP uses function pointers. And so these are a little bit harder to reason about that aesthetically. Hence, the dynamic step comes in really, really helpful here. All right. Then we perform a reachability analysis. Specifically, we look which API functions do reach any of those sensitive functions inside the PHP interpreter. So the PHP var unserialized, PHP output write will give us cross-site scripting attacks. And if you ever reach the execv system call, that's ripe for command injection. One note here, just because the reachability analysis said there is a path in your call graph doesn't mean that there is a vulnerability there. The interpreter could do sanitization. And so that's why the third step actually does validation. And so in the validation, we have proof of concept scripts that are being automatically generated for the first category for the insecure deserialization that we run. And therefore, we can identify those that are certainly vulnerable. Since we had more than an order of magnitude fewer results for cross-site scripting and command injection, we did that validation approach manually and have proof of concepts for all the things that actually work. At the end of the day, after the validation, we have a lower bound of all the vulnerable APIs within the PHP interpreter. We take this information and implant it into existing off-the-shelf analysis systems, including some that were published here in 2022, Fugio, the exploit system, was presented at USENIX 2 years ago. To essentially answer the question, well, we did all this analysis, does it actually help in a security sense, yes or no? Fortunately, as I can report, as we will see in the results, it actually does. And so how did we carry out our evaluation? We looked at 3 different versions of the PHP interpreter. Happy to discuss why we had to look at multiple versions here after the presentation. We extended 2 state-of-the-art vulnerability detection and exploitation systems, and then we evaluated the augmented systems on roughly 2,000 PHP applications and plugins to see what, from a new security perspective, we can gain in terms of insights. At the end of the day, what Argus detected was sets of deserialization sinks, and that set was an order of magnitude larger than the biggest set that prior work knew about or included. There was a Black Hat paper that knew about 29, I believe, deserialization sinks. And so if you look at the deserialization API column here, Argus was able to validate 284. So we know there are 284 deserialization sinks in PHP 7.2, meaning that the biggest knowledge base that we had previously was only covering 10% or less of the entire space that was out there. Similarly, we found 2 times more APIs that would lead to cross-site scripting injection vulnerabilities. All right, couple of more results in terms of what we learned from our downstream analysis. So we augmented RIPS and Zalm as a 2 static data flow analysis for PHP, and we augmented Fugio, ran it over our analysis data set, and these tools then detected pretty much unmodified 12 previously unknown insecure deserialization vulnerabilities, 1 cross-site scripting vulnerability, and 11 of those were assigned CVE identifiers. A couple of examples here. One example for insecure deserialization is from a very popular WordPress plugin, from the Feed Them Social plugin. And it turns out that the get meta tags API is actually going to deserialize your input. Conveniently, like the argument to get meta tags can also be a URL somewhere on a server. So you can very easily exploit the Feed Them Social plugin. I'm pretty sure that they changed this by now because this refers to Twitter, and Elon destroyed Twitter, so now it has to say X somewhere. So yeah, hopefully that no longer works. For cross-site scripting, that was in WordPress proper, actually. And so it turns out that if you use the read file API just like this, what will happen is that whatever the content is of the file gets directly written into the output HTTP stream for the client. So yeah, that's the finding that we had on the WordPress side. In summary, Argus analyzes the PHP interpreter to build a call graph to identify APIs that lead to injection vulnerability inducing internal functions. By integrating those new sets of sinks, so those newly identified API functions, we can improve existing vulnerability detection and exploitation systems to come to concrete new security benefits. And so the takeaway from all of this should really be, if you're doing data flow analysis, don't rely on manually created lists of sensitive functions if you don't have so, and Argus tells you that you do not have to do so. Our code's online, artifacts have been evaluated. I'm more than happy to take the rest of the time to answer your questions.